Hi, I'm Grant, and I build the most technologically advanced robotic can crusher in the world. My goal with this project was, I wanted to do something fun, but I wanted to make a consumer product completely from scratch. I also wanted to be multidisciplinary, work on all the various aspects, not just my particular specialty, software and embedded engineering, and do a little bit of everything. And I wanted to go wide on everything and push my skills as if I was a bunch of members of a team trying to build this and not go deep onto one particular project. So first, let me talk about the frame. The frame starts off with 3 aluminum extrusions. These are standard 2040 aluminum extrusions. These you just buy, they're pretty commodity. You can get them in any size you want. All the parts in yellow are parts that I 3D printed. I did do the design in FreeCAD, so I designed all the parts from scratch. I did not reuse any existing parts or things like that. These 3 white parts here, I actually got laser cut out of aluminum from Oshcut. Now, the bottom and the top are structural. This plate needs force to crush a can. So, I knew 3D printing would not have the strength. 3D printing, it's layered, it's laminated. They have what they call infill, but it's essentially hollow on the inside. So if you see that, it can like flex a lot under force. Initially, I thought I could do this at home. I've got a little cheap CNC machine. So I got some acrylic. This is cast acrylic. It's thick, it's totally solid. It's a lot less flexible than the 3D printed material. But even after I was getting into that, it just turned out it was still flexing too much and it was having trouble crushing the can. So I broke down. I've actually never done it before, but I went to Oshcut, a company out in Utah that goes ahead and has a hobbyist level laser cutting thing. It's reasonably affordable, and I got, these pieces made out of nice, strong aluminum, aircraft aluminum, 1/4 inch thick. They don't bend at all. It's, depending on your hobby budget, it's a little pricey. I wouldn't be buying something like this every week, but in the end, all 3 pieces, this piece, the base, and the top were $126 if I took the slow option. So I think it really added a lot to the project. I wouldn't do it all the time, but it is nice to know. And they do have a really great web interface. You just drag and drop it, the same as if you've done like a PCB design or something like that. So it was very like hobbyist friendly. So then we did have in my initial design, so we do have these motors, servos or stepper motors with threaded rods that move the platform up and down. And in my initial design, I did not put in these straight rods. So these straight rods provide some support, and I had to go ahead and add some bearing mounts. And what was happening originally was I didn't think I needed them because I wasn't trying to do something precise like 3D printing or CNC. I didn't care if something was 1/10 of a millimeter off. So I thought just these motors will apply the force. But what would happen is they would keep getting out of whack, and the platform would turn. Eventually it would like seize, and sometimes it would seize to the point where I'd have to like take these screws out. I couldn't manually get things leveled again, and just assembling and disassembling became to be a real pain. So I thought, well, I better add these rods and see what they do. They actually worked very well for that purpose. And out of everything I'm doing here, mechanical is probably my weakest aspect here. But what really surprised me was, once I added this and added this control, it made a big difference on the force and the ability to get down and crush the can. Even before, when I had this original aluminum piece that doesn't have those bearings, it wasn't quite getting there. But having that straight and aligned and at the right angles, it really translated the torque from these spinning motors into force that went down, and it crushed the can. So that actually made a huge difference. And now I see that they're more important than just for keeping the alignment right where it is. Next up, we have the control PCB. So this is the original one I've designed. It's a little bit Simple. I tried to get this one out quickly because I wanted to move forward. I am right now getting the second one manufactured that has some more power supply things. But the big parts on here are, I've used a Raspberry Pi Pico. Now that's a, if you don't know, it's a more of an embedded chip that Raspberry Pi has come out with. It's more competing with things like STM32 chips, things like that. It's an ARM processor, runs at 133 megahertz. Then I use these controllers. You can get these, they're kind of semi-standard for 3D printing. 3D printing boards have them, and you plug them in. And these particular drivers, which actually spin these stepper motors, are TMC2209 ones, and I picked those because they have automatic stall detection. That means they set off a flag. If you get it all set up right, you know, when the motors move in and it runs into something, it sends a message like there's an obstruction. And that's important because you need to home the device when you're using it. You need to, it has no idea where it is. It needs to figure out where it is when you boot up the device. So it has to go down to the bottom, decide that's the 0 point, and then from there it knows, you know, where it's moving things up and down, where the motors go there. And that actually worked out pretty well. The alternative to that is you have these like little limit switches, and they're mechanical, and you've got to screw them to the side, and like, you know, there's screws holding them in so they can move a little, this can bend a little, and even if you get them set up, they're not exactly where you want to detect, so sometimes you need to make accommodations. So I find these really annoying, so I wanted to go ahead and move to something a little better there. Now these drive the stepper motors, you know, the motors at the base of the unit, and they want, like, they'll run at lower levels, but in general, people run them higher, 12 volts, 24 volts, and these chips take care of that. You can sort of throw in an arbitrary voltage. It sends out some PWM signals, but the higher voltage, you get better reliability. So because of that, we had a bunch of 12 volt stuff running through here. This tells it what to do. It goes down to these. And then up here, I added these normal connectors, you know, which connect to the motors. But one thing I wanted to do is these stepper motors, they run pretty hot. Both these chips, you can see they have heat sinks on them. And one of the reasons you put them on risers is because they can get fried. And the motors themselves, even when they're not moving, if you have them on, they hold their position because they're magnets, and they will warm up, and you can like touch them on the side and feel they're pretty warm. So I really wanted to make sure that we weren't just continuously sending 12 volts to these things 24 hours a day. So probably the biggest design element here is I did set up, you know, you've got the power coming in here, and then I've got a little subsystem here, which has a MOSFET, which allows the power to flow. And then it's got another little MOSFET, which connects to the Raspberry Pi, and it controls. So basically the way it works is, in an unknown state, it cannot deliver power to the motors. You need to be powered up, you need to have a working Pi Pico, and the Pi Pico needs to be able to say, hey, I want to send these 12 volts out. And then on top of that, you know, that's the hardware solution. So then the software turns it on and off, and within the software, which I'll talk a little bit more about later, it actually has some power management stuff in there so that after 5 minutes, it just automatically shuts down. So that was my way of trying to prevent things from going on fire. On the simple board, you know, I added a little reboot pin. This mirror's messing with me a little. And I added a RGB LED and a button so that early on in development, I could get some feedback with knowing that things were working and programs were running. That's going to go away from a future version. Then up here is the serial connector, and that's gets to the control software. And then I went ahead and added a riser for pins that aren't used in case I wanted to upgrade, so that I wouldn't need to respin a board and wait 2 weeks for that to happen. Now these boards, if you don't know, you can get boards made. You need to solder them yourselves, but these days you can get them in China for $3 for 5 copies of the same board. And then if you want quick shipping because you're in a hurry, that's $19 to get DHL shipping. So for less than $25, you can get these boards, you know, manufactured and sent to your house. So that's really makes things a lot easier when you're trying to do this sort of thing. And I am making another one now that actually, right now, one weird thing is I've got the 12 volts coming in at the bottom, and then this still needs, it's an individual 5 volt power. So I'm making another board now that I've got the design settled down that has a switching regulator so that it just has one source of power going to everything on the boards. Okay, so the Pico, like I said, it's more of a competitor to like an STM 32. It runs at 133 megahertz at the max. It can run low power. It does have 2 cores. I did not use 2 cores in this project. And the one thing it had that was nice that I wanted to use is it has PIO, programmable IO subprocessors. These are 2 little subprocessors. They're very simple. They have a custom assembly language. I think it's 14 instructions. And what they're really good at doing, programmable IO, I think says it, they're really good at turning bytes in memory into GPIO signals and taking GPIO signals and turning them back into bytes. They also run independently of the main CPU, so you can get really extremely deterministic output based on the clock signal. Everything also goes, one instruction runs 1 clock cycle, so you can figure out exactly down to the clock cycle how fast your program is running. Also, because they are dedicated processors, things like an interrupt triggering won't pause them. They keep running as the interrupts are going. What I used them for was to create, so getting back, you've got these stepper motors here. They spin around, the stepper motors connect to the stepper driver, and those get a step signal. And the step says move forward a little bit. So you basically, to get a certain speed, you need to generate a square wave. And if you want the exact speed, that needs to be very precise. So I was able to write a small PIO program, 20 lines of code, something like that. And then you could say when you wanted the motor to move, I can shoot that information in. It will generate that perfect square wave to get the exact thing you want. And it still does have a little code where if you get the stall condition that I mentioned, it can catch that and abort and then report back to the main system that I did not complete my action. So that actually worked out pretty well. I was glad with the way that worked, and that was nice. On top of that, once I had the basics set up and had proved the motors were running, the next thing I did, among everything that I think is probably the biggest thing, is I wrote a mini control language. So you can sit there and you can write all this code in C, and it's very great to write in C or even the PIO assembly, but it's very hard to get things done. So it's nice and embedded to have very low level code where you know exactly what's happening, but then it makes it harder to implement bigger abstractions, like say a can crushing algorithm. So what I did to get between that is I have, this board is running low level. It controls the motors, it checks for things, it does the very low level tasks, and then it exposes a little mini control language where you can send it commands, for example, like move 110, and that would be move 100 millimeters at 10 millimeters per second. It can return status. It's very basic. You can set some parameters. You can't do loops or anything like that. And the idea is that with that, then I can write, I can have a core that runs really rock solid and then start building layer and layer on top of more sophisticated behavior. That worked out pretty well. I was pretty happy with that. It was nice that you could open up a terminal through the serial connection and just type commands into test, but I never really intended it to be like a human usable language. You've kind of got this, but I did want to expose something simple that could be parsed easily by the system and go from there. So then what I did on the other end on my computer is I created a Python bridge that talks to the serial connection. And what that did is that just abstracted all of the code away so that instead of saying like, here's a serial connection and here's this very specific can of like move in all caps and a space and 100 and a space and 10, and instead it gets a more Python style interface, so that you can do like, collide.move 110, and it will like even like throw exceptions, right? So if it hits an instruction, it throws an exception, and you're not dealing with like the lay and return codes that you deal with in lower level languages. And that was great. That really helped me develop much more swiftly. One thing that was hard to do is, so you do have this sensing, and what we're trying to do is like when this hits this, we get a stall detection. Now, because these are very general purpose chips, they have a functionality, but it kind of relies on you knowing how much current is flowing, so it's very application dependent. So you need to tune and program the right values into that. And originally, when I was very early on, before I had the control language, before I had the Python, I was just guessing here and there. Once I had the Python abstraction, I was able to make a really systematic program that would take, go up and down, like set the things too high so that it would stall on purpose, start lowering them, dial in, also do sort of a divide and conquer. So instead of going from like value 255 all the way to 0, 1 by 1 by 1. You know, we could go to 255 to 128 and then sort of like bisect the problem to make things happen quickly and run it over a broad range of speed. And it was really great to be able to like write that in Python and not have to worry about, you know, just all the little details you'd have to worry about if you were trying to write that in raw C. So I guess one second though, getting real, you know, this is a project for fun. There are plenty of open source software programs. Marlin's a big one for 3D printing, Gerbil for CNC machines. They have a language, so, you know, I was trying to do a little bit of everything, but if this was like a real product, there probably are a lot of off-the-shelf components I could have bought in terms of a board and in terms of an interface language. So just, you know, for this project, it was fun. I'm trying to like invent everything, but, you know, if it was something more real, I probably would have found something more stable and more mature. Okay, so after that, we have control, right? So we need a control screen. My idea was that like this is a consumer project. It needs a little kiosk, like something you see when you're pumping gas at a gas station. Like, hey, let's print fun facts about aluminum and things like that, and ask trivia, and maybe show annoying ads now and then. So for the main control software, I made up this little thing. I had a TFT touchscreen. That's just some Amazon special, and I'm powering it with a Raspberry Pi Zero, mostly because I had those. It is annoying that this market's getting fragmented and there are lots of shortages, and it's hard to just like buy the exact same thing you use for a product. And then to keep things simple, I did make a little breakout board that just connects the two parts together. Sticking a little much, and for the most part, this is just connecting one part to two part. I did add a little pot to like control the brightness of the LED, and I added a capacitor because it's a little bit far away from the power source to sort of act as a decoupling capacitor. And then there's a 4-pin connection, which brings the power up from the main board and also gives the wires for that serial connection so that they can talk together. Now this was a really simple board to make. I'm not too, you know, impressed with myself for making it, but it is compared to things I would have done in the past where I would have run wires everywhere or done something crazy. Once again, it's really great. You can get these made for $3 and anywhere from like $4 more to $19 for shipping, depending on how fast you want it. I also think, you know, I think some people do some amount of soldering and stuff like that, but don't feel like hardware gurus, and they kind of see people making PCBs online, and it seems like something you couldn't possibly do. Something like this, if you've been working with these or Arduinos and you've got all this stuff on a breadboard, I think something where you just like transplant that to a PCB and get it made, that would be a very good place to start if you're interested in trying to do this sort of thing, but are a little intimidated by it. Because it really is just like a, you know, placing the holes, connecting it, and drawing all these like little wires back and forth and getting that sorted. It's not the same as, say, having to figure out like what capacitor value do I need to filter power, and like which way, how does an MPN enhancement mode transistor work, and op amp, you know, it's very simple. And I think if you're at a point where you are like soldering things and you're doing things on breadboards, I think it's a very achievable goal to make a board like that, you know, if you're trying to level up on your hobby. So one interesting thing though is, so now I have this here, the Raspberry Pi Zero. It's running Linux, and then it's got the Python code, which can run and make things happen. And one thing that was interesting is I ran into some complications now that we're using Linux. So this display screen had a chip, an ILI 9834, I think, and there was this really great open source driver which you could plug in, and it would copy the frame buffer of Linux. So what that meant is it would take, you know, what you would have drawn on the normal screen of a monitor plugged in, and it'd move it to here. And it was designed to be like lightning fast. It was this, and it had great documentation. It was awesome. And I was like, that's great. I don't need to write my own routine to do that. But then I went to integrate the touchscreen, and the touchscreen had a DT overlay, a device tree overlay. So you got to put something so that then the kernel knows about it. And that broke the screen, the display. So then if I wanted to use the touchscreen, I couldn't use that library. And, you know, not a big deal, but I dealt with it. Another problem I had was, you know, I got everything working and running, and I set things up as a systemd service so that it would start at boot. You wouldn't need to sit there and connect and run a program. You know, it's a consumer product. You should be able to plug it in and it should be able to run. And for some reason, the systemd process wasn't starting up at boot, but then if I ran the command to start it up after it booted, it worked just fine. And what ended up happening after debugging and scratching my head was that there were UDEV rules. And this again, if you can't follow all this, that's fine. But the point is, it's complex. But so UDEV user device, it like sets permissions on devices when you plug a USB in. And for some reason, when the SPI device first got mounted, SPI, which is what's used to drive the display, it was mounted with permissions where only root could access it. Then somewhere in this boot up process, this UDEV rules thing runs, and then it changes the group to SPI. And then my thing was an SPI. So if you waited enough seconds, it would work. And then I was able to add code and fix that. And you know, so these are minor annoyances, and that's the kind of things you deal with a lot when you're writing computer programs. But I was thinking about it, what I think was really interesting about that is it illustrates like what is embedded programming, what is an embedded system. So embedded Linux is kind of like a Linux system, in my opinion, that doesn't just have a keyboard, a mouse, a screen. And then you get into these lower level chips, you know, like this, run 133 megahertz. It does not have an operating system. You're talking directly. You know, you're not running Linux on this. And then there are even smaller ones, you know, you get to some like at mega chips, they're running at like 16 megahertz, 8 megahertz. So why are people using these? Is it just because they're cheaper? And I mean, if you're producing volume, yeah, cheap, that's a big deal. But I think one thing is, as you get lower level and more constrained, you have a better understanding of exactly what's going on. And I think getting back to this, where I was able to use this PIO to write, where I know down to the clock cycle how the square wave is being generated. You can't do that in Linux, right? You might have your processor changing speeds to save battery. You might have something kick in. You might have some service. It's all the multitasking you can't predict. So it's great because there's a lot of abstraction. You can develop a lot of stuff. And for a lot of stuff, it doesn't matter that it's like that, right? You can't tell that like while your cursor's blinking in your Word document and you're typing that other things are going on in the background. You know, you might have a video game hogging the resource, but when you're trying to like control a motor, it's actually very important that things are deterministic and predictable. So one of the reasons, big reasons you push down to a lower level system and a lower level design and getting rid of an operating system, which seems kind of crazy, is because then you don't have problems like there's this process I didn't even know about in a tree of 58 things that happen if you look at the systemd boot level, and on top of systemd, there's stuff in init-rd and things like that. So I think as I got to the tail end after working with embedded, I dealt with some annoying problems. I was able to overcome them, but it was just in my mind, it was interesting to think about like, on the one hand, they're annoying and you got to deal with them, but on the other hand, it's a good example of why as you get lower and into more systems where you need more direct control, you want to throw away that garbage and deal with something that's now annoying in its own way, because now you need to program in a very low level, unforgiving language. If you get it wrong, your program crashes, you need to be ready for things to happen. But it's annoying in the work you do, but it's like much more easy to understand what's going on, why things are happening, and you don't need to rely on some Stack Overflow article. You know, so I guess that's one level, nice abstraction, complexity. You can do lots of crazy things, but then when things aren't working the way you want, it can be a real weird, unusual problem, completely unrelated to the code you're working on. Where here, not a lot of abstraction, not a lot of complexity, but you really understand what is going on with the system, and you really have, to a certain degree, full control. So that's my sermon for the day on that. So then we had all of that set up, you know, and I was able to write, I already had the Python interface. I was able to write some more advanced Python code. It would do things, you know, when it boots, it initially homes the device. Then when you press a button, you know, it goes through till it hits a stall, which means it's hit a can. Then it switches modes and it starts going up and down and crushing and making things happen. And, you know, it was really nice to be able to play around with that with Python and develop some really high-level sophisticated behaviors above and beyond the low-level things, as I've said before, that would be really annoying to write out like hundreds or thousands of lines of C. And then I also had, to deal with this display and the touchscreen. And this is one thing that was a little unusual because the Python, or not the Python, the Pi Zero is an unusual spot where it's definitely way faster than an embedded system, but it's still running a little slow, and it still only has 512 meg. So it's not at a point where you can like run easily a full desktop on it. So it was a little slower than I would have liked, but compared to an embedded system, it had way, way, way more storage space, right? Because I've got an SD card here. I think I have a 4 gig one. I could have made 8 gigs. So for the display, what I did is I had a program that pre-rendered all of the images I wanted. It used Python image library. It went ahead and, made all of these images ahead of time, and then it saved them both as PNGs so that I could look at them and in a very raw format. Now, the reason I did that is because then when this app is running on a underpowered unit, it doesn't need to do the horsepower there. It can just copy the data over onto the display and get things up in a reasonable amount of time. So, I'm pre-calculating, memoizing, whatever you want to call it. And that allowed me to sort of take advantage of the fact that it's not quite fast enough, but it does have a lot of disk space. And then there was a little bit to get the touchscreen working. I had to add a calibration routine. So if you bring up a system that you've never had before, some squares hit on the machine, you got to touch them, and then it knows how to figure out what part of the screen you're touching. But at that point, things were getting to be a pretty big breeze. I was seeing a lot. It was definitely big benefit. Early on a project, you're spending a long time, and like the motor spins a little, and you're like, yeah. Here it was really able to be like, oh wow, man, the can's crushing, or this is moving around, or this algorithm is working well. So that was very fun and easy to develop. All right, so I think that sums up all of the major components I wanted to talk about on this project. So I know everyone would like to see it crushing a can. Okay, and there we have it. That's the first round of this device. I think there are, several improvements I could do. There's some sophistication, but in terms of just getting it to a point where I had a single consumer product, I'm pretty happy with the results. This is available on GitHub if you're foolhardy or foolish enough to want to make this yourself. All the files to print out the 3D parts, all the files to adjust those, all the files for the CAD, or if you just want to send the Gerbers off to get PCBs manufactured, they're there. And if it is something, I don't expect a lot of people to make this, but I would definitely be very happy to talk to anyone trying to make this if you have any problems or need advice or anything like that. So once again, thanks for your time, and I hope you like the project.